Well, a warm welcome, everybody. Thank you for being here. No pressure to do this problem if you've already just recently taken the AP Calculus exam, the 2025 exam for this year. No pressure to put yourself through this again. But if you'd like, you can grab yourself a notebook, a pencil, or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And as I said, this is a problem from the 2025, that's this year's AP Calculus exam. I'm going to take you through these problems and see what could have possibly went wrong. Hopefully you felt good about what you did, and I really hope you used Desmos effectively, but I think you'll notice how Desmos doesn't get you the answer for every single point in these questions. It's possible that you get most of the points from the setup, which is what I like to emphasize here. So if you're going to attempt a problem again, go ahead and give yourself about 15 minutes. You can pause the video, take your time, be thorough. And when you're ready, you can unpause the video. Or if you just didn't feel like working on it and wanted to see how it was done here, that's what we're about to cover. Okay, so let's take a look at this. I've breezed through the questions just to see what kinds of parts they're asking about, basically, for each of them, but I haven't really looked into these. So it's kind of fresh eyes. Let's get started. An invasive species of plant appears in a fruit grove at time t equals 0 and starts to spread. And this function they give us, this represents the current amount of acres in the fruit grove that are being affected. So we're basically keeping track of essentially how much of this invasive species is around, even though technically it measures how many acres are being affected over a certain number of weeks. And it gives us the derivative. That's pretty nice of them. It can be shown that this is the derivative. Now they want us to find the average number of acres that are affected in part A. So what are we looking for? We're looking for the average number of acres. From t equals 0 to t equals 4. So how do we find an average value? That's going to come down to using an integral. So we're going to use the integral of the number of affected acres. And we're interested in that from 0 to 4. This is going to tell us the total number of acres affected over the 4 weeks. But then we have to divide it by 4 so that we get an average number per week. So we can just easily do that with Desmos. We'll put it in terms of x. We're going to take the integral from 0 to 4 of 7.6 arctan of 0.2x, and that's dx. Don't forget to divide all of this by 4. Okay, there we have it. So we have about 2.778. So on any given week, there are approximately 2.778 acres that are affected. Between the first 4 weeks, that is. Okay, and I guess I'll write acres. Part B, find the time when the instantaneous rate of change, so we need to find a time when the instantaneous rate of change equals the average rate of change. So you should recognize that relationship between the two as requiring the MVT. So we're going to say by the MVT, which we know applies because arctan is well behaved. It's smooth and it's continuous. We can just take the average rate of change here. We can set it equal to, so I'm going to say average equals to the derivative. We want that to happen at some time. So I want you to notice that this means C4 minus C0 over 4 minus 0, which is just 4, equals this 38 over 25 plus t squared business. Okay. Now how can I find the time and solve for that? There's actually a pretty good way to do this. If you just want to know when things are equal, you can subtract them and find out when their difference is 0. So I'm going to do 38 over 25 plus t squared. I'll probably put it in as x squared in the Desmos program, minus whatever this average comes out to be. And we want to find out when is this equal to 0. So let's just program the function in really quickly. We're going to say that c of x is this. Okay. And then we're going to plug in a function that says y equals 38 over 25 plus x squared minus, now I can just do this easily by recalling the function, c4 minus c0 over 4. And here I can see where does that cross 0. In fact, I'll remove the arctan function in a moment just to show you that's kind of what it looks like. So very smooth and continuous as well. So here we have a simple point. It's going to be at 2.154. So when t equals 2.154, that is when these times are equal. And that's going to be in weeks. They don't specifically request units, but it's good to know. A reminder that you'll want to round to the third decimal place here. So I noticed on the instructions it said accurate to 3 decimal places. So if you wanted to round 4 decimal places, I think that would be even safer. They're not going to penalize you for being even safer. Okay, let's look at part C. Assume that the invasive species continues to spread according to the given model. Write a limit expression. Oh, this should be fairly easy to write that. Write a limit expression that describes the end behavior of the rate of change in the number of acres affected. So the rate of change in numbers of acres, that's C prime. And then it wants us to evaluate this limit, which should be fairly easy. So we want to take a limit as t goes to infinity of not the number of affected acres, but the rate of change of the number of affected acres. So this one's kind of like not requiring a calculator. We're going to have 38 over 25 plus t squared. As t gets really big, the denominator there is going to get really large. And so the overall fraction is basically just going to go to 0. So at some point, this will not be affecting the fruit groves, but for now, it seems like they're affecting about 2 acres at a time, almost 3 acres at a time. Okay, last part, let's look at part D. At time t equals 4, after the invasive species appears, measures are taken to counter the spread of that invasive species. So after 4 weeks, there's some kind of response, and the function is defined by this. AT equals CT minus the integral from 4 to t of 0.1 ln of x dx. This models the number of acres affected by the species over time from 4 to 36. So we have however much the invasive species normally would affect things minus this sort of corrective factor because we've taken some measures. We don't know what we did, but measures were taken. Sounds so grave. Okay, the question here is, at what time does A attain its maximum value? And so they're giving you an interval of time. This comes down to finding an absolute maximum or a minimum. So we're going to have to consider A4, which just equals C4. We're going to have to consider A36, which would be C36 minus this integral from 4 to 36 of 0.1 ln of x dx. And then we also have to try to find some critical points. So we're going to have to take the derivative a prime, which is just going to be c prime. But then we have to take the derivative of this integral here. So I'm going to sort of do that carefully. Let's suppose that capital F of x is an antiderivative. I could have just said that 0.1 ln x, the derivative of that, but I'm deciding to write it this way. Is a derivative of 0.1 ln x. So suppose that it is, then we're looking at the derivative with respect to time, technically, of f of t minus f of 4. That's using the fundamental theorem of calculus, I believe part 2. And so this is just going to turn into c prime minus 0.1 ln of t. That's because the derivative of capital F is just going to go back to ln times 0.1. But the derivative of this is a constant derivative, that's 0. All right, so here we have a prime of t. And we need to find critical points, right? So we need this to equal to 0. And again, we can do that pretty easily by just writing this on Desmos. Oh, maybe I should have kept that. Is there an undo? There is an undo. So this is going to be c prime. Remember, this was still c prime, 38 over 25 plus x squared. But now we're going to subtract 0.1 ln of x. And we're going to see where from 4 to 36 does that hit 0. Okay, so we definitely get some kind of a point there. It seems to continue going downwards, so we don't have to worry about it crossing again. Just good to make sure that it doesn't cross again. All right, so what was that? 11.4417, you can write it. If you're nervous about the rounding, you can put 442, I'm sure to be fine. But if you put 11.4417, and this is in weeks, that's also worth checking out. So our other candidate here is going to be A of that time, A of 11.4417, which is simply going to be C of 11.4417 minus the integral from 4 to 11.4417 of 0.1 ln of x dx. Okay, so we're going to compare all of those to see which one is maximum. Now, C4 is pretty easy to do. We can just see what is C4. All right. Now, for A of 36, we're going to need C of 36, but we're going to subtract the integral from 4 to 36 of 0.1 ln of x. Remember, don't forget to put parentheses here. You want to make sure everything there is contained by the parentheses. Okay, that's a pretty small value at the final time of 36 weeks. And then let's see what is C of 11.4417 minus integral from 4 to 11.4417. You guys get the drill. Of 0.1 ln. Oops, not NL, ln. Okay, that looks to be our maximum value. I mean, you can't just copy and paste on the exam, but if you just had to write down, C4 is 5.128. So let's see, this is going to be, let's write it in red. 5.128. This one was 1.734. Am I making that up? 743. It's like, am I hallucinating? 743. And then we have the head honcho here, which is going to be 7. I didn't even remember that one. I just know that it's maximal. 7.317 is totally fine. 7.317. And so that's going to be our maximal amount, which means that a time of 11.4417 weeks is when it's going to attain its maximum. We can say A of t is maximal. And so that's going to be the roughest week on the fruit groves, because that's apparently when the maximum amounts of acres is maximal. There we go. Okay, so yeah, that wasn't too bad. We did have to use Desmos a couple of times for integrating what kinds of things could go wrong. Now, if you accidentally take an integral here of the derivative of c prime, instead of c, yeah, then that could solve your problem there. The limit process is not too difficult, but again, if you're not careful to see that it's a limit on the rate of change, and you accidentally do that on the equation c, it will be different. You notice that, right? It's a limit expression that describes the end behavior of the rate of change, not the overall number of acres. Okay, and then finally in part D, using the fundamental theorem of calculus is not too tricky there. It is just sort of a nice replacement, just becomes 0.1 ln of t. But in some cases, that could be a gnarlier function. I think you can imagine how that could be a tougher function to deal with, or maybe one of the limits is strange for some reason. And then applying what an absolute maximum is, which means out of the candidates, the endpoints and the critical points, those are the possible contenders for an absolute maximum. You just plug them all in, with the help of Desmos, of course, and then you compare. All right, so this first question, hopefully it inspired confidence in you and didn't scare you away. And you got a chance to see how we did it here. That should do it out of me. Not too much more blab. I'll see you guys next time in the void.